Well, hello. Good afternoon, everybody in Switzerland. Good morning, depending on your time zone. Still some more people popping on the screen, but I'll just start welcoming you and then hand over the word for the introduction of our talk today. So we are actually very happy to welcome you at the Smart Living Lab online today, virtually, for one of our invited talks. So we are at the Smart Living Lab, which is a research center dedicated to the future of the built environment, where we study building technology, we study energy systems for the building, for the neighborhood. We study user well-being and comfort, user interactions with the buildings, and of course also the design and innovation processes in the field of architecture, construction, and building technologies. So I am Martin Gonzenbach. I'm the operational director of the Smart Living Lab. So I have the privilege of coordinating the activities of this quite a unique center, since we are a center that is bringing together various research groups from 3 different universities in Fribourg, a city in Switzerland. So we have the 3 universities. There is EPFL, which is at the Federal Institute of Technology of Western Switzerland. And there's a satellite campus of EPFL developing in Fribourg together with the Fribourg School of Engineering and Architecture and the University of Fribourg, who joined forces to create this center called the Smart Living Lab, which is still quite a young organization. We are in the process of developing our own experimental building that we'll start constructing this year, and that will host about 130 people from different disciplines, from architecture, from engineering, from structural engineers, mechanical engineers, also data scientists and software engineers working more on the digital aspects of the building systems, building design, and also automation and control, and the energy management aspect. So it's a very, very rich network of competences. And I also should not forget to mention that we also have a group specializing in innovation management and business, and the one specializing on law and construction law and the legal aspects. So it gives a very interdisciplinary spectrum of disciplines that are all addressing the challenges of the future built environment. And so we have this series of invited talks, which normally take place physically on our premises at the campus Fribourg. But today, well, for obvious reasons, we are holding the event online and have the privilege of having quite a wide audience. So it's very exciting to have actually people attending from so many different places internationally today, and also the privilege of having a very prominent speaker, Zoltan Nagy, who is today based in Austin, Texas. So it's very early for you, Zoltan, still in early morning. And I thank the group of Dolana Kovalik, Amireza Haidari, who took the initiative of inviting you for this talk today. And we'll hand over the mic to Dolana for introducing the talk.
Thank you very much for handing over. And actually, we are very pleased to have for the first seminar of the year at Smart Living Lab, Dr. Zoltan Nagy. And Dr. Nagy is an assistant professor in the Department of Civil Architectural and Environmental Engineering, as it was mentioned, at the University of Texas at Austin in the United States. And he's directing the Intelligent Environments Laboratory since 2016. His research interests are in smart buildings and cities, renewable energy systems, control systems for zero-emission building operation, machine learning, and artificial intelligence for the built environment, complex fenestration systems, and influence of building occupants on energy performance. So these are all topics that are really very closely related to the research activities at Smart Living Lab. And Dr. Nagy received his PhD in robotics from ETH Zurich. And prior to joining UT Austin, he was a senior scientist at the Architecture and Building Systems Research Group at ETH Zurich. So, and it's my great pleasure actually to welcome him back to Switzerland, at least online. And it's a great pleasure to actually ask him to present the latest developments on model-free controllers in his research team. And now the floor is yours, Dr. Nagy.
Thank you, Donala. Thank you, Martin, for the very nice introduction. Amir Reza for the invitation to speak. I'm excited to be here. Let me quickly join my share my screen, and then we can get the show started. Good morning, good evening, afternoon for everyone, wherever you are. See, happened here. 1 second. Huh. Oh, there is a procedure you have to follow apparently. So, okay. All right. So, let's get the show started. So I'm watching the yeah, as Martin wrote in the chat box, I'm watching the chat box. If you have a question, feel free to type it in there. I can speak, forever, because that's what I'm usually do. So if you want to interrupt, it's much nicer to have a conversation. I have about 50 slides, 40 minutes, so roughly. And then we can have a conversation. But if you have a pressing question, feel free to interrupt. Okay, so Solana mentioned we'll talk about intelligent systems, intelligent environments using reinforcement learning. This is not a technical talk, so it's more about, for me, like inspirational, motivational. These are the things you can do rather than the mathematical details. You can read the papers. I'll show you some links for that if you're interested in the technical details, and we can chat about it. Quickly, just how this happens to go from robots and micro robots to architecture. For those of you familiar with the nest at EMPA in Dübendorf, you may see this facade go up. This is in the ETH campus on Hang, but they currently installed that facade in the HEIA module. So that was basically my postdoc project to develop that facade that driven by robots or by small robots who develop these actuators that are pneumatic and then inflate, and so you have this highly flexible facade that you can actuate, very detailed. It generates electricity and shading and then modulates lighting and so on. And so we did a lot of the hardware, and it took a long time. Obviously, everything takes longer than you plan. And so by the time I left, really the interesting part to me, what I wanted to work on was the control. So how do you run this thing? Like there is like 50 actuators on one of those things. And, some might say it's been over-designed with the actuators, and that's probably true. But even if it wasn't, the question was, how would you run this without, spending tons and tons of money on engineers to actually run it, but somehow try to learn it. So anyway, so there is this path between, intelligent systems you can see in the first part of my studies, and then architecture. And so that's kind of like, how my whatever you see is shaped. The group I have, Martin mentioned interdisciplinary is important. This is an interdisciplinary field by itself, trying to understand energy systems, control, bringing in machine learning, but then applying it into the built environment. And ensuring, energy efficient operation, understanding people in the built environment. And so drawing students from different areas is very, very important. So you can have these conversations in the group between architects, but also, CS, computer engineers, and also civil and architectural engineers, which is our core department. So this is a picture from last year. So now it would be just Zoom boxes, but this looks a lot better. You can see actual people. So we try to mix up what we do. The research we're trying to do, and I'm always trying to think about how we sort of like present this, like what are we doing, and really the question we're trying to answer is this: like, what is a smart building, right? You see this a lot. Well, not the smart cars, but like everything's a smart building, smart cities. It's kind of like a buzzword, but nobody really knows what that means, and so. For us, it means understanding how buildings are occupied, understanding how people are utilized, understanding that there's a lot of data being generated but not used, and so trying to use that to improve. And that's kind of like where the smartness comes in, like making decisions to improve, operations and comfort down the road. In a nutshell, there's two topics that I'm very sort of like, highlighting when it comes to that. One is intelligence. Again, this idea that you make decisions, based on data, and human responsives, not to forget, right, that it's us people who are not responsible, but that's the reason why we have energy use in the buildings, right? If you wanted energy efficient buildings, zero energy buildings, to switch off everything, it's great, and you sit in the dark. But you have to create it in a way that does not impact intended use, which is to support people's lives. So that's kind of like our vision. One thing I wanted to show, because this is cool, and so this is from during my PhD I was doing some fun projects, and this is with a friend in the physics department at that time, in the AI lab in the University of Zurich. And this was striking to me for an interesting reason, as obviously there's nothing to do with buildings, but what you see is these shapes that are, carved out in a funny way. There's magnets in them. So here you can see there's fixed magnets, and then these shapes here that are floating are like just, floating magnets on water. And so what happens is, once these things get close, as you can see up here, they initiate a reaction. And so this is a model for like an enzymatic reaction, basically. So once the actuator comes close, the enzyme comes close to that molecule, it creates a switching in that molecule. But what is interesting, and the reason I'm showing it, is because there's no, control system in this. All you have is the knowledge of the interaction, in this case magnets, the way to use that interaction. The shape of these devices here is, very unique. It's very specific. It has to deal with distances. It has to deal with these pathways that you have. And so understanding this interaction is key to design simple systems which will exhibit complex behavior down the road. And so that's kind of like what I'm trying to have my thoughts guide by, right? Buildings are really complex, and what you need to do is really, really complex, right? I said there's lots of data. There's many different layers, from individual zones to multiple buildings, if you go all the way to neighborhood scales. And so understanding the interactions, but then is one thing, but then designing the systems in a way that you create complex behavior that is intended but not complicated to do is like the key, like for the motivation. So this is as background. What my group does can be roughly grouped into three areas. So we do a little bit of work on all like machine learning fields, right? Unsupervised learning, the clustering algorithms, smart way to pre-process the data, run the data, transforming time series into images, doing deep learning on the image and transforming them back into time series to understand a little bit or to apply some of the advances in image processing, which is pretty cool. Supervised learning methods are trying to integrate, building or urban scale simulation models by just looking at images and integrating neural networks to extract information from that. That's pretty in an early stage, but it seems pretty interesting. There's a lot that I grouped down here, building IoT devices, measuring the environment, things are cheap. You can measure lots and lots of devices, but it goes back to the initial question, what do we do with all that data? And how do we make interesting decisions? So just measuring stuff will not get you anywhere. It generates more data. And so that's not the whole purpose. And so today's lecture here really on reinforcement learning, which on this figure, it looks like it's a quarter of what we do, but really more than half of what we do. This is, when I started, those were the two projects that we really pushed. And so I will try to focus on these two today, and then, get you to excite. The whole purpose of this talk to get you excited about reinforcement learning and why it's cool and why I think everybody should do it. And because, there's potential for it to be very successful down the road. Of course, I could be wrong, but let me talk about it first. So reinforcement learning, it's been all over the news in the last couple of years, especially after DeepMind has beaten Lee Sedol, one of the best players in this Go game. And the main reason for that, and you know, we had Deep Blue, I guess, by the IBM computer being Kasparov in the 90s, or you know, or late 90s or early 2000s. I don't remember, being on chess. But chess is different from Go in that chess is very clear. Like there's rules and you can, you know, compute. And so with brute force, brute power, computing power, you can beat anyone. Go, the advantage of Go or the disadvantage of Go, why people thought it would be hard to do, is because it's very intuitive. And so you could not pre-program moves in a sense. And so we really had to understand the game and have a feeling for it, so to speak, right? So it was thought that it would be only humanly possible. But nevertheless, so AlphaGo, DeepMind, sorry, created this program AlphaGo, and then in a series of games, I think beat Lee Sedol. I think Lee got one game in, and AlphaGo beat the other one. There is a Netflix documentary if you're interested in the story, so you can watch it. It's pretty cool. So how does it work? Well, in general, we have a control system, and so that the agent down here, you know, receives information called states from the environment. This can be anything, you know, your features, your data that comes in, and based on that data, you want to make decisions and then take actions in that space. And then the environment, or you know, the way the whole environment or the whole system is set up, provides you with the reward. And so you use that reward to shape your decisions, you know, to take forward and to make better decisions in the future. It is kind of like optimization. You know, the reward function is your objective function. So there's lots of elements to that. In a nutshell, right? It's basically formalizing a trial and error process. So you do something, you fail, you get some feedback. You do something else, it gets better. You get better feedback, and then you keep going until, you know, you improve, and then you make your life better. It is also, you know, going back, one of the very first initial thoughts or visions of the whole artificial intelligence movement was not to pre-program, right? It was to give computers the ability to learn on their own. And so as Turing puts it here, right, you don't program to simulate the adult mind that's developed, where you know exactly what the task is, but you create one that can mimic the children's mind, which can then grow with the task or learn over time, right? And so that's kind of like the idea behind the RAL. The reason it didn't came along until today, like the last 5, 6, 7, 8 years, has been tremendous progress. The main reason for that is computing power. The ideas that we're talking about today were around 50 years ago, right? And so now today we're in a position that we have, you know, DeepMind and all the computing power of Google, and have run simulations that were not possible 50 years ago. There's also lots and lots of algorithms. You know, if you open the literature, this word reinforcement learning will open up a bag of worms. There's a big debate in this area here. So model free, between model free and model based RL. Model based, what that really means is that, you know the environment, so you understand where this is going. So you can poke the environment and say, well, you know, if I do this, what will happen next time? If I do this, you know, 5 next steps, what will happen 5 steps down the road? It's very similar to like a model predictive approach, where you say, oh, you know, here's my trajectory for the next 12 hours or whatever your time horizon is. And then you take one step in that direction. Model free, on the other hand, you know, is the approach where you don't know that. And so you really create this interaction that I mentioned before, like you're trying to learn and explore the environment by poking it literally and trying to understand what's happening. So, you know, Jolana mentioned before, I'm very interested in model-free environments for 2 very simple reasons. If you have model-based environments, there are better ways to do control. There is no need to do RL if you can have a model. There are advantages, you can optimize even better, but the real advantage of RL to me is the framework that you don't have to do that. And so if you don't have to do a model, you can do things like, it's very scalable if you can create it, right? You can have hundreds of buildings that you can start with the same setup, and eventually you'll get your behavior for each of them separately. And that's really the power when you think about RL in the built environment, to me. I don't want to go into all of these, algorithms here. That there are some famous ones, DQN, Deep Q networks, and SAC, the soft actor critic ones. This is the one that we're using recently because it's very sample efficient. And so it's learning the fastest and the most robust from the data that we're presenting to it for our purposes. So not in general, probably, but for our purposes in the built environment, especially on energy models on the building, on the urban scale. It seems to be the most efficient one. And we're doing a lot of comparisons, and I'll come to that in a second. Just like being even able to compare is one thing that is, is a fundamental problem right now, because everybody's doing it. Everybody gives you like this talk, what I'm doing now, it's awesome, and here's what we did. But there's very little fundamental at the bottom to actually try to go back and compare all these different environments to see which one is the best one, or which one is more efficient. So. Okay, so let me show you again, like it's a motivational speech. So here's an example from one of my first explorations. This is in Zurich. You see, this is a paper from 2015. So the work was even before that. So it's probably about 10 years old. And so this is the house of Dr. Leibengut, professor at Zurich, who renovated it. You probably have seen it around the B35, it's called. And so it's this house is several stories, apartments, and renovated with geothermal heat pumps, geothermal boreholes. There's solar thermal collectors on the roof. And so Philip, who is here, was doing his PhD on model predictive control of these devices. So there was a model, in Simulink that was for providing all the systems for it. So we could use that to simulate the building, not for a model predictive control, but just not to, we have to go to the real building and then, not mess it up. And so we used this model with Lei, who was my master's student at the time. And so we said, well, why? I mean, it's all there. Let's just try it. At that time, RL was not really moving in the literature. There were a few papers. There was one big work in the mid 90s or early 2000s in Dr. Moser in Boulder. But really it was not. And then another person in Boulder, Dr. Henze, those were the two initial works in the built environment, but it was really low laying, quiet in that area. So I was like, yeah, well, it's there, let's try it out. So what we did, we took this model and then we basically said, let's look at the thermal loops. So there's these 3 thermal loops in that building. One is a solar thermal collector here, right? The PV panels generate the thermal, the hot water when they get hit. And so you provide them with some reward if you generate. Then there is the borehole, which extracts heat from the ground and then provides it to the space heating environment via the heat pumps. This is an interesting one because it can extract heat from the borehole and provide it to space heating, but it can also use the heat from the solar panels to regenerate the ground hole. And then there is the other one, the last one, which is actually providing the space heating into the building. And so again, we did a lot of simplifications, a lot of assumptions, but at the end of the day, it was a pretty cool system, and it was running fairly well. And so what I was interested in is looking at, well, what can you get, right? And so we had real data. So real data over like 4 years of weather data that we could use. You could literally run 4 years as it would happen in reality, provided how the building model is the same or applicable. So the 3 curves you see, the red, green, and the blue, are 3 neural networks that we used, and then the dashed line is the reference controller that was set in the building, rule-based controller, which is what they used in the setup. And so Lei and I just sit down, thought about it a little bit, did some stuff from the literature, and come up with this approach that in the beginning you do this exploration phase and you really try to teach, and then as you move into the next phase, you learned a lot. You don't do a lot of updates anymore because that destabilizes the system quite a bit, and so you just slow down a little bit. So you see in the first year, at the end, man, it's like, okay, if you show this to engineers, they're like, yeah, no, this is not good enough. But then it continues, right? Like, because, you know, here is like 20% off. You should compare it to the blue one. The green one did well. Anyway, so if you continue though, the year after year, right, you see two things. One, gets a lot better. And then, so every year, basically, you outperform. And then after this is third year, it's robust against the structure of the neural network. So this this is like hidden layer size and output layer size and things like that. So we just experimented with different sizes, and so it was pretty robust against that. And you learn quite a bit. And so some people come to me and they say, yeah, Zoltan, it takes 3 years to learn. I mean, come on. Or like even a year, like, come on. I'm like, yeah, but the building's standing for 20 years. I mean, that you have that time. It's not a robot. It doesn't have to be microseconds, and nothing really happens if you don't perform, other than people get cold. And so that's what you have to protect against, is that you always perform to provide the heating. But whether you learn in a year or 6 months, it's really not. To me, at least, should not be the factor that you compare this for. And so what was interesting is, right, you have 10% increasement every year, and then Philip, who was doing his PhD on MPC at the same time with the same model, got the same improvement, but sitting on it for a while and having to run like a PC, a dedicated PC to run the optimization, which was pretty cool. I mean, cool in it, not for Philip, but it was pretty cool for me as like a motivational sort of like impact. I'm like, this is interesting. There's something here. By the way, Philip is with BS2, that company that promotes geothermal heat pumps and solar thermal collectors, and he's doing their operational automation, building automation system. So that's pretty cool. So anyway, so I'm like, okay, this is interesting. So this was when we almost a year before I left for Austin, and then as we came here, we immediately started to push this topic quite a bit heavily. We presented an improvement of that system in a more general setup. Take a heat pump, take some storage. Here's the building. Can we learn, to control that when or where not you run the storage to provide heating and cooling to the building. And so, our first approach was a bit of a mess and patchwork between all these top softwares that are out there. We used CitySim as a baseline for the computer model, which comes from EPFL. We worked with Jerome Kempf. I don't know if Jerome's here, but anyway, so he helped us with that part. Jose, who was the lead author behind this, actually did his master's at EPFL with John-Luis Cartesini. So there's a lot of connections here. So I'm happy to be intellectually back now. So with EPFL, anyway, so that we use that, and then the whole RL part, runs into the standard libraries of TensorFlow and Keras to make them usable, and then what was really the big challenge here is to make all these connections. And for everybody who tried to do code simulation, what happens is you try to move, one file is an output for the other, then you have a supervisory file that takes the output from one and makes sure the other one is there, and then you end up with a huge mess. So it worked for a while. This was good for us to, show the proof of concept, and moreover to also, confirm what I just told you before. It's like, again, you can do what you want to do. You can improve without the knowledge of the building itself. More importantly, what we found, and you can read it in the paper, if your systems become more and more complicated, not complicated, but complex. So if you only have a heat pump, you will not gain a lot of impact. But if you start having a heat pump, some storage, solar PV, the interaction between the systems becomes a lot more complex, and teasing out the details and the energy efficiency of that is a lot more hard if when you try to do it directly. And so having a learning approach really helps to accommodate for the individualities of the building. And so as you're thinking towards decarbonization and electrification of the end users in everything, and also adding electric vehicles into your buildings, it does not get a lot simpler. It even gets even more complicated, right? So that's why I think there is something here that might be interesting to evolve further down the road. The other things that we saw, you can adapt to changes. So we simulated retrofits halfway through the building. We updated the U value, we exchanged the windows, and then you could see that the system can continue to adapt and improve its behavior. And so that's kind of cool. And again, it goes to that initial figure that I mentioned. Like if you improve, if you understand how things interact, and if you learn from that, you can create complex outcomes for the systems with very simple setups, right? Because what you have to do is engineer the interactions, but not the individual systems, right? Okay, so this was, again, motivating further. It was like, okay, this can go, but really what I wanted to do, what I wanted to study is this. You have a city, and in 2020, somebody has like a smart thermostat and maybe has PV, but then legislation happens, and all of a sudden everybody will have it, right? Next year, people start to get connected, EVs are coming, more people have PVs because your neighbor has them, so you have to have them. You see, I don't know, IKEA starts selling PV, so everybody goes to IKEA, buys a couch and buys a PV battery on this and on the roof. So all of a sudden you get this lot of potential in the built environment, right, to modulate and to create this microgrids and to create distributed generation and to create really this system that can offset what the grid is doing, or support it, right? And so that helps us with transitioning from, in the US, gas-based, mostly power plants, to more renewable-based power plants, which are not, happening at the same time when you have your demand, the duck curve. However, if you have distributed generation and storage and cars, which can also act as storage, you can go towards offsetting some of those power plants. So creating a system like this with the setup we had before was really, really not possible. So we had to simplify a little bit something and create an environment where we could study this. And so what we did, right, this was Jose's PhD thesis, basically, is to create the CityLearn environment, which would allow us to study this in a more strategic way, focusing on the controls and not so much on the actual building systems, not building system, but the building themselves. So what it is, in brief, right, in OpenAI Gym environment, and the Gym environments are used by RL researchers in the computer science community to standardize environments, right? So basically, it's like I don't want to say black box, but it's like an environment that has an API. So it just says, give me the states, I give you the actions, provide me with the reward. And so you can give this environment to almost anyone, and you can work on the controllers without having to deal with the buildings. And so what that does is, not that you should know about buildings and building systems, but if you don't have to set it up your own way, you don't have to do that procedure that I mentioned before this one, where everybody tries to do their patchwork. And what you have then is an environment that's comparable. And what you have then is something where we can say, well, I ran my algorithm, it runs, it takes 2 days and produces these results. And but mine runs in half a day and it's a little bit better. And so clearly mine is better because the environment we compared it is the same. And so this benchmarking approach, I think, is very crucial to pushing this field into direction that can actually create impact, rather than everybody doing their own sort of like little environments. And so again, like I said, you can export out buildings, you can focus on the building systems and their control, and you can do all kinds of cool stuff. We have done things where we have one controller that knows everything, like usually like 10 buildings, one controller that knows everything on buildings, or you can do things where nobody knows anything about the other ones, or you can think about what information do they have to share in order to improve their behavior. So like things like transfer learning is a topic that starts to pop up. And in detail, or in specifically what this is a way to do energy storage control, because really the question that this is modeling is you have thermal storage in the buildings, and so whether you use your heat pumps to drive that storage or bypass the storage directly, or you use a storage to address your heating and your cooling loads. That's what the algorithm does. And then you can add PV arrays. This is not the most recent picture. We're currently adding electric batteries and electric vehicles, so you can do the full electrification thing to it. So with that, you can do some cool things. Here's an example of 9 buildings. These are DOE buildings, the standard buildings. So we can, again, standardization, right? So there's 5 multifamily houses, 2 with PV, a strip mall, I think an office. This is a McDonald's, and then I don't know what this was, small office building or something. So anyway, some commercial and some residential. I think the load's about half residential, half commercial. And so we run these together. You get an idea what you can do, or what the data is that's running through. The states that the algorithm gets, things like month, day, what hour of the day, what the environment is, temperature, humidity, solar radiation. You can do forecasted. We do it forecasted with some errors in it, 5%, 20% errors in your forecast. The examples I'm showing you is hot and humid climate. That's where we are. So we have non-shiftable loads, some solar generation, some of the buildings have that, and then you're charging the domestic heat water and the chilled water storage. Again, you don't know anything about the buildings, and you start the buildings randomly, and you don't exchange information for the buildings. The only thing that you do is you provide a reward that is proportional to your energy use. And so there's a component for each building that is your own energy use for every hour. And then there's a component to that that's a collective one for all the buildings. This is not the most sophisticated way by any means to create a reward function that comprises like a common approach, but it's the simplest one to see whether that makes sense at all even, right? So let's see where it gets you. So here's what you can see what this microgrid, this 9 buildings, generate or require. So the spring fall demand is here. This is without any control, right? And then the summer peak, you have here the afternoon peak. That's because it's a hot climate. So that's a cooling load for the AC units. And then the winter load is pretty flat because there's nothing required. So the first thing you would do if you were to add those heat pumps, you would optimize it, and you would try to do something like, for the highest COP, coefficient of performance. And so that would usually mean you try to optimize those heat pumps to run, early in the morning when your COP is the highest, you charge up your storage, and then that's where you see the peak here. And then you run them through the day, and then you probably charge it up a little bit later at night again. So what you really do is you shift that peak to another time. Like there's not much, lower here. It's also not much lower here. So the demand is pretty much the same. The peak demand is almost the same. It just happens at a different time. And here, in fact, you increased it in the winter, which is strange. It is fine during the day. This offsets the duck curve, so that's pretty good. So this is what we have. If you do it in a smart way, so the orange one is that the impact of the reinforcement learning controller and having some storage in the system and some sort of smartness. You see what happens is that the orange curve and then the gray or the shaded area is like all the buildings, right? And so you see that band is a lot more horizontal, especially in the summer. Like it's really, if you look at it, well, if you draw the lines horizontally now, it gets horizontal. But compared to the green and the red one, you can see that it's a lot more straight, and that's interesting because that means it's the energy or the power that it needs from the power plant is pretty constant, which is different from what we have today, which is that you have a gigantic peak in the 4 o'clock in the afternoon in the summer because everybody turns on their IC because it's really hot, and so this helps a lot to avoid building new power plants that you don't need and running those that you have at different times more efficiently, right? And that's pretty cool. And you remember what I did this, I didn't know about the buildings. I didn't know, how you start this environment, and I didn't even have to exchange any information. So there is nobody needs to tell people what they're doing. So it's quite interesting. So again, obviously this is not ready for prime time, but it's quite an intriguing result to say that, you can flatten that curve borrow the name from another field that is problematic these days. But we can flatten the energy demand curve quite substantially if we have the right tools in that environment. And I think that's pretty cool. And that's kind of like, you know, what I want to take away from this is that this is possible without having to have very complicated controllers and supervisory things. There is more, so I will not go through this if you're interested in more. So after that, what I just showed you, we also worked a little bit on, well, what if we do some little bit of an exchange and it helps stabilizing learning, and you know, it gets even better results. If you do have some information sharing between the buildings, but it's still privacy preserving, so like just the aggregate and then making decisions based on what you know from other buildings. So you can read that in our BuildSys paper. I'm happy to send that. Anyway, but the point is, now we can compare this approach with the previous approach and see what will really improve upon that, right? And then that's really the interesting thing. I don't have, I think, results on that. The other thing we can do is compare the same environment, you know, with different reward functions. So we looked at, you know, what if we don't share any reward between the buildings and we have them just work on their own? How does that compare to, you know, if we share that aggregated reward between all the buildings and give that as a reward? And again, it improves to the RBC. There is some issues, you know, so it's not the best way, but again, like trying to understand slowly where we're going with this and in a systematic way is very, very powerful, because you can then say, yeah, look here, this is what's happening. And then what's funny is, so I'll go to my colleagues at computer science who study RL like theoretically, and I'm like, well, this here's like 100 buildings, run your algorithms and see which one of those will actually do something in the real world or could do something in the real world. And then that's really cool. So they're taking this and then just applying their own controllers that are just coming out, because, you know, these guys, every week there's a new algorithm, new RL that is better, faster than every other one before. And so we can't keep up with that unless we have an environment where we can compare what one before, and then others can use the environment to actually run those algorithms. So I think there is a lot of these you know, this push in this area will be helped by an environment like this, whether it's this or some other one, where we can compare results and compare nodes and understand, you know, the impact of our research. If you're interested in this, yeah, so there's a BuildSys paper. You can also go to YouTube. Jose's PhD thesis is online, and you can watch it, and you get all the details. Or his BuildSys video is also online, and you can learn all the details about this. And you know, it's all on GitHub too. If you need to see the code, it's all ready to go. Some cool features with CityLearn, and I have a small other topic after that. Hopefully I have time. Anyway, so you know, we organized the challenge last year for people to run their algorithms and compete. We'll do another one this year. People start using it, which is cool. I see papers coming out every now and then. We had a workshop in the fall at BuildSys on RL for the built environment. There were a few of those also using CityLearn. So, you know, it's a momentum. All the national labs here are starting to use RL. So it's not going away for a while, and so it's nice to be part of, I think, this for now, and so hopefully a team where it's going. For about 5 minutes, I think I have 5 more minutes. I wanted to switch gears because there's another topic that for which RL is really interesting, which is when you come down to occupants. And the reason that's interesting is because people are not predictable. People are really a messy bunch, right? Like you cannot deal. I mean, it's once you have to deal with people in buildings, oh my God, it's hard. And so trying to think about like, how can we create this environment where we can, you know, satisfy the people without annoying them, but also not, you know, using energy that we don't need, is hard. And so RL allows you this interaction directly, right? It is built into the system that you can interact with a computer, you can provide system, you can provide feedback, you can provide reward functions. And so you can actually teach, you can try to teach the controller to act the way you want it, so you're comfortable and it's not annoying you. And then when you're not there, or when you have taught it how you're comfortable, it can control the building systems. in a smart way, right? So that's the other line of research, right, on the occupant-centric control using RL. So we had, lighting control we did, and then HVACLearn. So Martin is asking, how efficiently can RL be tested and compared in simulated environments versus real buildings? That is a very good question. So not many people are doing real buildings. So that's as with anything, right? Like it takes time. And so there are a few great places like, yours are set up to do this kind of research. EMPA is another one. At Nest, I do some work with IBM in Australia where they also have access to buildings where they can test it out. But in general, people are reluctant a little bit still because you tell them, well, we're just going to do stuff and then we're going to reward that computer somehow. And they're like, well, wait a minute, what are you doing? So there is a like a little bit of a need to go one step further when you deal with real buildings, which is to explain what you're doing in a way that the building managers also understand it. And so you need also the buy-in from the building managers, and that's actually where this is going as well a little bit. So we were set up to run this experiment. So we talked with building managers, campus managers. It's a building, like it was 50 offices, I think. We picked 30 here. It's in building the perimeter offices. They're all individually controlled with their own thermostat, with chill beam, so we can address everyone perfectly. So what we're trying to do is this human in the loop approach, right? We would monitor devices, the environment, and pick the thermostat. We would give feedback, whether they're too hot or too cold. That's all. And it could be this, it could be a device, it could be a thermostat, it could be a button, whatever. There's some interface, right, that you generate feedback from. And then, you gather the data, you provide information to the building managers. That's the second layer in the human in the loop. And then they approve or not updating, the set points, heating and cooling set points in the building. And this is great. But, we built all these devices and then we deployed them and then we had to shut down. So this was literally the week before we were ready to test the experiments, which was, of course, not fun for the student doing his PhD research on this. Anyway, so the point is, these days it's hard to do human in the loop experiments in buildings. So what we did is we pivoted a little bit and we did a simulation model instead. Unfortunately, we had to do that, but I'll show you. And again, that was pretty cool. So what we did, right? Oops. What we did was first trying to understand what the states would be. And this is a tricky one because what we're trying to do is really make the people comfortable without knowing what comfortable means for them. And so we're trying to guess it, and we guess it from their feedback. So when they say they're too hot and too cold, we monitor, right? So you get these distribution, like when they push buttons. Oh, it is this hot, or this is the temperature when they start pushing, I'm too cold. This is the temperature when they start pushing, I'm too hot. And so you get this distribution, and then by analyzing that distribution, you can create set points, right? And so that's kind of like how we're doing it. So this creates cooling and heating set points to the people, and that serves as states. And then the thermostat actions are basically increasing or decreasing set points, 1 degree up, 1 degree down. And then, then you keep doing that. And so because we had to simulate it, we did it in a simple office. It was a heating environment in Chicago. And then also we had to simulate the person. So we did the best models that were available. It's like a thermal vote, and then according to some probability model. So as the temperature increases, it's more probable that you will complain and things like that, or decreases. And so by just running different versions of these models, looking at different people, we can still study that algorithm. And so we did the Energy Plus, which is another advantage now, because then you can run this for buildings. And so then you can run it what the impact of such a model would be in a building design, like what's the percentage of this control basically in a building. So you can see here the results. First of all, should I build this up a little faster? So the left one, here, this is the energy. The blue curve is the controller, and the green one is the reference. So that's like a set point, a fixed set point, which is usually what the building managers do. So this is this part. And then so you can see on the left-hand side the comfort hours. So the comfort hour, discomfort hours, a lot reduced through the HVACLearn for the cooling control compared to the reference. You also see here the number of button pushes. This is just to simulate to see, like, it's an indication. The more button you push, the more unhappy you are. Of course, nobody will push the button 300 times. It's just in the algorithms, some like an indication, like how do you see how it happens. And so it is a lot less in the HVACLearn environment, which is cool. That is for cooling. For heating, we were like, this looks interesting. So the discomfort hours are similar. And these are runs over multiple times, right? So not just once, but maybe 20 times or something like that. That's why you get these distributions. And then the heating energy is not really substantially lower. So we're like, okay, this is interesting. I wonder why. And so one thing why is because of an artifact. We think the way building simulation models run, Energy Plus runs, it starts in January. And so basically in January, you know nothing, and over time you learn, and you see how, and then in the summer, there's no heating, right? And so that you don't learn anything. And then in October, November, you actually learn quite a bit and you do better than you did in January. And so, and then here it's the opposite. In January, it doesn't matter what you do. And then you learn slowly as it gets warmer that you need to cool. And so the performance is a lot better. So my hypothesis is that if we started this in July, it will get a similar result. And here we just have not had time to test this because, well, people graduate. And so I had to move away. But essentially, you see that you can learn again to adapt to that person and adapt to being comfortable, and also save energy without actually knowing what that person is doing, or that person having to specifically say something like, oh, I need this kind of temperature. Or just like, oh, it goes up and down, and we can guess it. Well, we can infer it. Okay, so that bring me to an end. This is why I like RL. To summarize, model free, which means it's cheap to install; scalable, which means you can build it to many buildings at the same time. You can initialize randomly usually, and that means you can deploy quickly and easily. Off policy, I didn't talk about that, but the off policy algorithms lets you learn from past data, which is really cool because that you have often. It is robust in a sense that you don't have to do it from the beginning. You can transition to it. Buildings come with their own controllers, so there is a baseline already. You can use that and then build on that. You don't have to start from scratch. And it's effective. It's good. It really works as far as we can tell, especially when things become complicated and complex. If you want to see more, go to our YouTube page. Right, this is the new year, right? The new way, everything's on YouTube. So go on, our videos are on YouTube. It's a lot of information, a lot of build-sys stuff from last fall, and some PhD defenses. And then also from the workshop RLM that we organized, like 2-minute teaser videos, and the whole workshop's here. You can watch everybody's work if you're interested. Okay, thank you. With that, I hope I did not run over time. I do have more time if you all want to stay longer, that's fine. But sorry, it was too long. Anyway, I'm ready for questions.
Yeah, thanks very much, Zoltan. Very inspiring and exciting talk. So yeah, let's open the floor to questions. Raise your hand or wave on the screen or whatever.
Okay, Lissy asked, what conferences would you recommend and where one could get feedback on energy demand response and RL at the same time? So that is an excellent question. And I don't think there is one. This is why we started that workshop, RLEM, that actually was the purpose of that. So build-sys often works on RL and energy. The main challenge is if you go to building specific conferences, the RL part will often be not, I want to say weak, but it's not going to be the focus. If you go to a CS conference, the RL part would be really strong, but the building part might be a little, And so it's really hard. And so I say follow the people who know a little bit about both. So look at people who do, who publish, who work these days, LBNL, ORNL, NREL, they all have works in this and they know everything. They know a lot about buildings and they know a lot about AI. And so those where they publish is a good place. build-sys is my favorite, and e-energy. Those are the two ACM conferences, computing conferences, but focusing on energy. Hopefully that answers your question. Other questions? So I'll put those into the chat. Regarding the HVAC control, were those approaches applied to operating buildings? Can it be used to inform help designers during the design stage? So I think that's a very good question. So we have not, I'm currently trying to work with a friend at EMPA actually to run it there. So hopefully that'll work out. But again, like if it was not for COVID, we would have had a year now of running it in our building. We did run it with lighting control. So if you go and search for a paper called LightLearn, it's essentially the same thing, but for lighting. Lighting is a little bit easier for that purpose. Using it for the design stage is also possible. So the June, who did the HVACLearn project, he's a professor now in Arlington. And so with him, we continue working on a simulation environment. So we have a paper coming out soon where you can, plug it into Energy Plus and use that as a sort of like mechanism to understand the impact of that. So you can pretty soon, people will be doing that. The whole NX79 group, I believe Delana also knows those people. There's like 100 people around the world scattered that deal with occupancy-centric building control. My part, I'm leading like the implementation people, but there is a whole other group that only deal with the design process and how, occupancy-centric design impacts the design stage. And so like all of these things that we're discussing and how it can be used earlier on is definitely something that we'll learn a lot very soon. Amireza, raise your hand. Yeah, go ahead.
Yeah, thank you very much for your presentation. I had basically a question about the adaptation capability of the reinforcement learning, because when it comes to the reinforcement learning, we usually talk about the adaptation as the major advantage of the algorithm over the existing. And it's quite useful now, especially with the COVID, because notice the behavior of the occupants has changed a lot. But what I see in the papers is that they usually train a model for a specific duration, and then they deploy it on a lower computation device. So if basically during the training phase, we do not see a special event, like let's say we have trained the algorithm during the typical days, and now we have the COVID situation, which is not seen in the training phase. Is it still adaptable to the new situation, or it should be always learning?
Yeah, so I think that is a good question, and it's a hard one. So there is no yes and no answer to this, right? It depends a little bit, I think, how you set it up and how people start to set it up. So if you use the RL, there's two ways to do it, like what you said, right? You can, one approach is that people do is we use RL so we don't have to have a very expensive controller on the edge, so to speak, right? So we pre-train it, we deploy it, and we forget about it. And that's one way to do it. I think if you want to use the full power of RL, what you want to do is build in some updates over time, right? And so the mechanism of, if you see new data, you have to update your controller. So that in your design and deployment phase, you should include that. So in the first example I showed, right, the first paper, the old paper, we had a very, the way the updates were done in the first year, and then years 2, 3, and 4 were different. So in the first year, we really tried to push the controller and learn a lot with new data. And then we were happy and we said, well, let's not keep learning. We just, if you see something that's unusual, or if you see something that's better, add that to your training set, and then learn that, right? And so that way you don't destabilize the whole thing, but you can add the new stuff. You also, and I did not go over this, but how you learn, like what data you use to learn, is a whole topic on its own, right? Like you create batches, you make sure those batches are representative. And so as new data comes in, you can use new data if it's not been seen before and use that and retrain your models, right? Yeah. Or update them in your models. So I think this is why, just saying I'm doing RL is tricky, because it's a can of worms. If you're thinking about deploying on the real building, you have to have it in place. Like, okay, maybe there is a pre-training phase, and then after that, maybe there is an updating phase every now and then. Maybe it's not every hour, maybe it's every week, right? You gather the data, and then once a week you update it. That's how we did the HVACLearn project. The thought is you update once a week, maybe twice every other week or something like that, because you don't have so much data, right? If you just push a thermostat,
Yes.
nobody uses that. So thinking about how you update the data in the real world is very, very important. I think it's one of those topics that are getting overlooked, and that what Martin mentioned, when you go into real buildings, like something's going to hit you in the face really hard, and that's one of those things.
Well, what we would like to know, right? Just
Right.
one last, I'd say last question we can take in the plenary session from Roberto. Then, of course, those of you who want to stick online and continue chatting together, it's perfectly fine if you have the time, but some of us will have to leave to other meetings since it's 2:00 now. So maybe let Roberto ask his question, and then we will conclude the plenary.
Yeah. Thank you. It's very quick. So thank you very much for the great talk. I really enjoyed it. It's more a technical question related to this. So how much of the RL performance is somehow affected by the choice of the reward function? I think there is a kind of relation to that. You have to tune this.
Everything. I mean, no, like probably half. I mean, the reward function is basically the place that you have as a designer, right? That you have to tweak to get the behavior, right? So because you don't program the behavior, you have to provide the incentives. And so it's literally like, what is the incentive that you're trying to generate? What is the behavior that you're trying to create, and what is the incentive to that, right? The ones we used is very simple, like energy. You could also provide like the shape of the curve, right? Like if you can parameterize that, maybe that's a reward. Like, and you try to flatten that, like that's all of that. I think again is one of those things where, trying to figure out what is best and fastest is probably useful. So the reward function is a designer's input. So that's where your understanding of the system is the one that will matter a lot.
Well, that's a good takeaway message for those who want to start playing with those systems. Thank you very much, Zoltan, for this great talk, and thanks everyone for joining us online today. As I said, please stay online together if you do have time, but well, some of the hosts will have to leave. This is my case, unfortunately. But also stay tuned to our threads of news of the Smart Living Lab on the social media, Twitter and LinkedIn. There will be more events, more talks also online, since we will have to continue in this mode during the next weeks, and hopefully not for too long. But it was a pleasure having you all together today, and have a good afternoon or day for the US.
Yeah, there is another question I will answer right now.
Okay, but I have to leave.
Thank you, Martin. Thank you. Bye-bye.
Cheers.
So Sarah, you asked whether there was convergence issues, and yes, and that goes to the other thing that Robert mentioned. So one thing is you pick the reward function, but the other thing is what algorithm you pick. And as I showed in the beginning, there is a whole array of those. Can I pull this back? Oops. So there is a whole array of these, and it turns out some of them are more suitable to the problems we're working than others. So, like we tried the DQN and DDPG in the first paper that I mentioned, and those were really tough. They did not like at all. It was hard to converge. And then for the SAC algorithm, it's based on entropy and like a little bit more information theory, not Q-learning straight. And that one really helped a lot. It's a lot more stable, and it helps a lot to converge a lot faster. So I don't know if that answers your question, but I think that also, goes to say that let's not call it RL, but really compare apples and apples. So the same algorithm on this, or different algorithms on the same environment, to like really compare, apples with apples. Good question, Sarah. Thank you. Yeah, thanks for coming. Is SAC available in CityLearn? Yes, that's how it's built. So you can go and check it out, written up there. And also the advantage of using the gym environment is that other people publish their controllers in the gym environment. And so you can almost like translate, you know, not one-on-one, but very quickly the other new controllers. Maria, so what are you interested in for RL?
Yeah, basically, we are working on the like hot water systems that can adapt to the occupants' behavior. And we are already installing some sensors on the buildings to really monitor the occupant behavior and make a balance between the energy use, the comfort, and also another thing in the hot water systems, which is not seen in the previous studies, is the hygiene of the hot water systems, because like every once a day we should superheat the hot water to make sure there is no Legionella bacteria, but it is also in contrast with the other objectives too. We are implementing this to make a balance between these algorithms. But as you mentioned, I'm working on tensor force and DQN, but it's very unstable. Like every run, I have a different answer and very sample inefficient. So I think based on your suggestion, I will move to CityLearn and try if with SAC I can get a better result. But basically with CityLearn, is it possible to integrate it with other softwares like Transys and so on?
Oh man, okay. No. No, I mean, yes, I don't know. Let's see. So it's running in Python, right? So now you're getting into how do you co-simulate the whole thing. So if you want, you probably do the opposite and see what you want to run and come up with the gym environment for that problem rather than trying to use CityLearn to your setup, right? Right. Because it might be a little tricky. I mean, to what we have to apply to what you think. But if you send me more details, I can take a look.
Sure. Okay. Basically, already in Python, I have the possibility to integrate trans. Yeah, well, thank you.
Yeah. So yeah, I'll happy to look at it. There was a question in chat I'm trying to read. The idea is to integrate RL with schematic design, so there will be collaboration with architects. And can you integrate the system on existing buildings easily? Dana, yeah, easily is always the question. So that is my hope, right? So the problem with real buildings is that they're not set up for smart control. They're set up for whatever Siemens wants you to have, and so there is actually a lot of startups out there trying to link between the data coming from a BMS system or an EMS system and being able to apply RL or any other algorithm, really. And so if maybe you've seen these works of, it came out of Berkeley a long time ago, like, all the time now on brick and mortar and those schema, where you basically try to create a, what is it called? So the structure of they're trying to map the structure of the building systems semantically or on the ontology in the computer program, so that this data stream is an air handling unit, this data stream is a temperature, this data stream is a fan speed. And so once you have that link, you can run a lot of algorithms on the other side because you know how you translate that. The challenge is always before that, like you have tons of data and you don't know what they are and you don't know if they're clean. But once you have that translation, either the building managers have to figure that out, or you have to do it, or there are the startups that are doing that. And so once that is done, you can run anything you want, basically. Let's see. I don't know, Dana, did I answer your question? It was a little bit yada yada, but I can try again a little bit later. Then Nicola says, do you think RLC will catch and take over modeled PC control as the most promising building control technique? Nico, that is also a very good question. I think, okay, let's see. Probably not overtake. I think what we will see is a smart link of the two. So like a merging. There's a lot of work in MPC and a lot of good work in MPC, right? Especially if you think about individual buildings, not necessarily large, microgrids and larger, but individual buildings, MPC is really, really strong. So a lot of the work that people do now is trying to push the development of the needs for developing models, right? To lower that. Once you have that, it's pretty cool. And also the engineers understand it and the building managers understand it because you know exactly what to do, right? And so there is a lot of people started to do things like MPC with RL, right? There was Build Sys 2019. If you go and look, the best paper award went to one of my colleagues at Carnegie Mellon, GNU RL, which basically took a very simple MPC model and a very simple RL model and combined the two. And so the advantage was you had the very simple model, meaning you only have the format of the model, right? You don't know the parameters. And then you use RL to basically identify it and improve it. And so that kind of thinking where you give it a structure and then use RL to improve it, because of advantage of RL, is probably going to be very efficient in real environments because it has the advantage of both worlds. If you look the RLM workshop, if you go and look at the papers, some of the people there try to do physics-based RL or physics-based neural network constraints, like things where you try to bring your knowledge to the playing board, but then use the advantages on the other side. And so, marrying basically the best of both worlds. And the reason I personally like the full-blown model-free approach academically, because it's pushing the boundaries, it's trying to see how far you can get, and then when you get other models, you see how far you're missing or how much you're missing. Yet, in real world, I don't know. We'll see. I want to see that as well, right? That's why we organized that workshop, and we had that debate. If you watch the video, there was one person in there who said, I was doing MPC for the last 10 years, and what you guys talk about here, trying to get a better, trying to get a better, yeah, thank you, Marilena. Good to see you. Thanks for coming to my talk. Anyway, so at the end of that, at the end of the RLM workshop, we had this debate, and the guy goes like, I was working on MPC for 10 years, and you guys talk about how you can, learn without models or, simple models and whatnot. And we had that debate in MPC 5 years ago, 10 years ago, and I see the same direction here now. And so, and that's a very, very exciting thing academically and also technically, because it means that, we're hitting a wall with both topics. And so maybe the integration of both will be the interesting one. So I'm trying to work with him now, because I think those are the interesting questions, like where can we really improve things. Let's see, Alex. Yeah, I might contact you about potential application. Yes, please do so. All cool. I like big stuff. We'll go moving into bigger urban scale here as well. So that's cool. Nice.
I have another question about the reward.
Go ahead.
Did you face a kind of a sparse reward a space, or it was like a reward in each estate that you gave to the agent?
Yeah, you do have the space reward problem. So you the CityLearn, you can give reward every hour, right? So it's not really a problem. You run into a problem more when you're thinking of people and getting feedback from people, and how often you want to get that and how you want to use that. So what we ended up doing is, like I said, we kind of tried to work around that. And so the CityLearn does not have that really problem, because you can give reward at every hour, because it's the energy use basically. With the building, with the HVACLearn and the LightLearn, we did not do the updates at every hour, but once a week, right? So you gather all the data, you pick the data you want to use to train, and to update. And so then your reward is not necessarily sparse anymore, but you can get an aggregated reward for that week or something like that.
Okay, thank you.
It goes back to what Robert said before, like that, how you design that reward function makes so much, things better or worse. That's really key.
Yeah, thank you.
Yeah.
Hi, this is Javier Arroyo from K11 University. Thank you very much, Professor, for your great talk. I also do research on comparisons of different optimal controls for buildings. And I was wondering if during my PhD, we are developing the BOP-test framework. I don't know if you heard of it. Stands for Building Optimization Performance Test. And just didn't want to miss the chance because it's so related to your work of asking if you were aware of it. And also was wondering how reliable are the building models in CityLearn? Is it something you have taken a lot of care about, or is it just simplified models that you're using?
So no, actually, we thought a lot about it. So the building models that we use, and I didn't go into detail for that. So the building itself in our part is pre-simulated, right? So, and you can use whatever you want. So the ones that we have now are Energy Plus simulations, and so you whatever the output of that is however good that gets. So and what we did was to basically try to come up with thermostat settings that make sense. So NREL has these RESTOC database where you can learn on like how people use the thermostats, how people use appliances. So it's really not just standard setup, but it's more diversified, right? So when you have many buildings, things don't happen at the same time because otherwise it's not diverse. What is simplified a little bit is the systems. So the thermal storage, the PV systems, because those are the ones that you control. And so those are written in the Python code directly by us. So you can see them in the code. We open it, right? So you can look at them. We do things like, the PV systems react with the weather. So if it gets warmer, the temperature drops. I mean, the efficiency drops, right? Things like that. And we also will do similar things with the electric batteries when they're added, is that, you don't just charge, you charge and then you charge slower, like things like that. Like the power curve is different in efficiency. So we did a lot of work to get realistic into this so that they're not like some artifacts based on the simulation models. And also you can switch. So in the first run we did, in the very first paper, I showed CityLearn, SimCity, CitySim, right? That's a whole other environment, but you can use the outputs of those also to run CityLearn. You just have to translate again. And there's no difference in that.
Nice.
And yeah, I'm familiar with BOP-test. I'm actually on the advisory group. I just almost never make it to the meetings.
Okay, cool. It will be very nice to merge both, right? Like having BOP-test, because BOP-test is more focused on individual buildings, but we are taking a lot of care of having reliable models and also on the reproducibility of the key performance indicators so that they are computed the same way, to having this benchmarking framework. And you are more at the district level, so it would be cool to have like BOP-test buildings working in the CityLearn framework as well.
Yeah, no, I think BOP-test is exactly what we need. It will allow us to compare controllers, right? And that will be perfect. So hopefully that'll look cool. Say hi to David. Let me see him.
Yeah, thank you.
Thank you. Good. So if there are, Miresa, you has left your hand up, but that's from before, I guess. Okay. So also, okay. Yes, I mean, if you want to get more, get in touch, let me know. Go to our website, go to our YouTube page, subscribe. Yeah, anyway, shoot me an email, follow me on Twitter, whatever, send me an email, get in touch. I'm happy to talk more. It'll be fun. Thank you.
And thank you very much, basically.
Thank you, Professor.
Thank you so much.
Thank you.